Energy is part of reactions and can be taken from reactions and used for various things. Now, energy can either come out of or go into reactions, and the energy that comes out of or goes into reactions can be used to do things like phase changes. Energy is either in the form of potential energy or as kinetic energy. Potential energy is stored energy, and kinetic energy is the energy of motion. So fast gas molecules have lots of kinetic energy, and a cold solid has very little kinetic energy because it's all dependent on how fast the molecules are moving. The total energy in a system cannot change. So if energy leaves from one part of a system, it must be going into another part of the system. This is called the law of conservation of energy, and what it says is energy cannot be created nor destroyed. All that happens is that it's moved from one place to another. Therefore, potential energy can be changed to kinetic energy, and kinetic energy can be changed to potential energy, but the total amount of energy always stays the same. Energy can be expressed in several different types of units. Two common units are calories and joules. A calorie is defined as the amount of energy that it takes to raise 1 gram of water by 1 degree Celsius. This, of course, is liquid water. If you have gaseous water or solid water, it takes different amounts of energy. Another way of expressing energy is in joules, and a joule is smaller than calorie. 4.184 joules is in a calorie. We often will use both kilojoules and kilocalories, and it's rather easy using the kilo prefix to go from kilojoules to kilojoules to 1,000 joules, or kilocalories to 1,000 calories. You know how to do that after being familiar with the metric system. One thing that I'd like to bring up here is we're already familiar with the word calorie from food. A food calorie is written with a capital C. A capital C actually means a kilocalorie. And so when we talk about units of energy that come from food, we're talking about calories there, and it's not the same as the amount of energy that will raise 1 gram of water by 1 degree Celsius. In fact, 1 food calorie will raise 1,000 grams of water by 1 degree Celsius. It's much larger. When we talk about food calories, we're talking about the amount of energy that is stored in the bonds of food molecules. We have two options that we can do when we consume a food molecule. We can either store the food molecule on our body, which many of us do on our hips and thighs, or we can use the energy that are in those food molecules for movement or for metabolic processes. When we're looking at the different types of food molecules that we consume, we have rough estimates for the amount of energy that are in those bonds. In fat, we have about 9,000 calories, or 9 kilocalories, which is 9 food calories per gram of fat. And in carbohydrates and protein, a gram holds about 4,000 calories, which is 4 kilocalories, or 4 food calories. Using these values, I'd like you to pause and try this problem and figure out how many food calories are within one French fry here, and then there's another problem after that. Go ahead and calculate that and then resume the lecture. One French fry having 1 gram of fat and 3 grams of carbohydrate. Well, we start with the amounts of the nutrients, and then we do a conversion based on our rough estimates. So 1 gram of fat will hold 9 food calories. 3 grams of carbohydrates will hold 12 food calories. The two of those together give us 28 food calories. Go ahead and try this problem. Press pause and then press resume when you're through doing the problem.
The first thing we need to do in doing this problem is first write down all the nutrients that are given to us. So we write those down. Next, we convert them to energy, how much energy they provide to the body. And we already know how to do that for the individual ones using the amount of energy stored in each type of molecule per gram. Now we sum this up, and that gives us a total of 2,450 calories. Used in a day is 1,620. So we take the difference, and that gives us 830 calories. 830 calories can then be converted to fat. We take 830 calories, and 9 calories will be stored in 1 gram of fat, and so then we can convert it to 92 grams of fat.
Here on Earth, we're familiar with 3 common states of matter: gas, liquids, and solids. They differ in each other in the amount of movement that the molecules have. In gases, they're moving very fast, and they have large distances between each other. In liquids, they're still moving very fast, but attractive forces have started causing the molecules to hang close to each other, and so they stick together and they do not move far away from each other. They're still moving very rapidly, though. In a solid, molecules are still moving, but rather than moving past each other, they're staying in place and jiggling and wiggling in place. Now we're going to look at energy and how energy and phase changes are related. When a process requires energy to be absorbed in order for it to occur, we say that the process is endothermic. So when ice melts into water, we have to put heat into the ice for that to occur. So we say that's an endothermic process. When energy is released by a process, we say that process is exothermic. So when we burn wood, heat comes out of it, and we say that process is exothermic. When we're looking at phase changes, we're looking at how the physical state of the substance changes. So there is nothing happening to the bonds in the molecules. The only thing that is happening is how fast the molecules are moving and how tightly they adhere to each other. When we go from a solid to a liquid, we call it melting. And melting is endothermic because we have to add heat in for it to melt. When we reverse that process, it's called freezing. Freezing is exothermic because as a substance freezes, for instance, when water goes from liquid to solid, it must give off heat in order for it to freeze. It seems rather counterintuitive because you think, well, the ice is getting colder, but the reason that the ice is getting colder is that it's giving off its heat to something else. To go from a liquid to a gas is called vaporization. Going from a gas to a liquid, it is condensation. It requires heat to vaporize something, so that is endothermic. And when a gas becomes a liquid, it must give off heat, and that is exothermic. When steam condenses on something and becomes a liquid, a huge amount of heat is transferred into the substance that it's condensed onto, And so you can sometimes feel that when steam condenses on something, you can feel that it gets much warmer. You can recognize that that is an exothermic process. Going from a solid to a gas or a gas to a solid is called sublimation or deposition. Sublimation is endothermic. It requires heat to take solid molecules that are tightly adhering to each other and put them into the gaseous phase where there's no intermolecular attractive force. That heat is required to break those intermolecular attractive forces. Deposition is exothermic. As a gas deposits and becomes a solid, it gives off heat to its surroundings. This diagram is called a heating curve, and it shows how temperature changes as heat is added to a substance. When we have a solid, we can heat it up and the temperature changes in linear fashion until we hit the melting point. At the melting point, we can no longer cause the temperature to go up because all of the heat that you're adding in goes into melting the solid, so the temperature does not rise until all of the solid is gone. Once all of the solid is gone, the liquid then will increase in temperature in a linear fashion according to how much heat is added until we hit the boiling point. When you have the boiling point, at the boiling point, you have the liquid and the gas both present, and the gas cannot get any higher than the temperature of the liquid, which is at the boiling point, until all of the liquid has been converted to gas. Then, if you confine your gas, you can heat it up further and cause the temperature to rise. This means that if you're at the melting point, you have both the solid and the liquid present. If you're at the boiling point, you have both the liquid and the gas present. The temperature of the solid and the liquid are at the same temperature at the melting point. The temperature of the liquid and the gas are at the same temperature at the boiling point. So if you have a glass of water that has that has equilibrated, you can't just mix ice and water together and have both of them be at 0 degrees Celsius. But if you mix ice and water together, the two substances will come to the melting point after a time occurs. It doesn't matter how much ice you would have in there or how much liquid water, they both will be at 0 degrees Celsius after equilibration if there's both liquid and the solid. The same principle occurs at the boiling point. There's a similar curve for cooling. It's just the reverse of the heating curve. And there you can see that you would have the same thing happen as you cool a substance. There's really no difference between this curve and the other curve. The only difference is the direction in which you look at it. Be sure and do problems. Do the in-text problems as you read, and do the following end of chapter problems. Worksheets for this chapter have been posted online, and there are online quizzes posted for this chapter also.